Hello and welcome to what might be a special edition of Cracking the Cryptic. A few weeks ago I took on a puzzle called Phenomenon by Darth Paradox, and it took me nearly 3 hours to solve that puzzle, and we're going to release that video onto the main channel tomorrow. It's been a Patreon bonus for the last couple of weeks, and Mark suggested that I should continue to try and give our patrons extra content in the form of, these diabolical solves. And we've had a lot of requests recently, bizarrely, to try this puzzle, which is called Broken Secrets by TotallyNormalCat, a constructor I hold in the very highest regard, one of these geniuses in the world of puzzles, and frankly a fairly terrifying character, because every single puzzle I've done by TotallyNormalCat has left me sort of gobsmacked. Now weirdly, this puzzle, I don't quite know how I didn't have a go at this whenever it came out over 2 years ago. And I think I must have been sent it at that time, but I don't remember it. And the reason I think I must have been sent it is that it does refer to somebody called Simon in the flavour text. So TotallyNormalCat probably had me in mind when constructing this. I can't be sure, but I think it's fairly likely. Anyway, I've looked it up on Logic Masters Germany. It's had I think 10 solves ever, and yeah, so it's clearly a very, very difficult puzzle. Although the rule set's a bit mad, but it's very understandable. So I thought I'd have a go at this for you now. You might never see this because I might not be able to do it, but I'm going to try. So why don't we get cracking and see how we get on. Broken Secrets by TotallyNormalCat. These are the rules. When Simon was young, he used to hide his secrets in 9-cell cages. On his 45th birthday, he decided to revisit his childhood toys and found out the cages broke. Help him put them together to reveal the secrets of the universe. Any resemblance to actual persons, living or dead, or actual events is purely intentional. Thank you, TNC. Rules. Normal Sudoku rules apply, so we have to put the digits 1 to 9 once each in every row, every column, and every 3 by 3 box. There are 18 cages in the grid. I'm not going to count them. I'm sure TNC is right about that. Each cage has exactly one partner. Combined together, they form a 9-cell cage, and numbers must not repeat in a killer cage. Numbers on a thermometer must strictly increase as they move away from the bulb, and cells with grey squares must contain even digits. So I think the main point of this is that, yeah, those two squares have to be even. Digits have to rise as we move along a thermometer. So if this was a 3, this would have to be at least a 4. It's not slow thermometers today, which is what I was dealing with in the Sandra and Nala puzzle in yesterday's video. Normal thermometers. But the key is going to be, we have to combine, so that cage, for example, there, that is a 5-cell cage, and somewhere in this puzzle must be a 4-cell cage that amalgamates with this 5-cell cage. Let's say it might be that one. And these cages together have to form basically a cage with no repeating digits in it. So this is a virtual 9-cell cage. It's a fascinating idea, isn't it? And that's all the rules. So do have a go. The way to play is to click the link under the video as usual. But now I get to play. Let's get cracking. Now what I'm going to do first is to find out... Oh, what's that doing? I just double clicked on that cell. Oh gosh, this is Sven. This is Sven doing magical things, isn't it? So Sven somehow made it. I don't know how he does this, but when you click in a cage, it highlights all of the cages that are the same size. So, okay, so let's make those green. So they are 3-cell cages, so they have to amalgamate with 6-cell cages. That's a 6-cell cage. I'm going to double click that. Now, what colour should we make that that's going to be very distinct? I might make that grey. And then that's going to give me 5-cell cages. Let's make that blue. And I'll make these orange then. And that is all of them. And so our job is to pair up, for example, this cage with one of the grey cages, this cage with one of the grey cages, this cage with one of the grey cages. And simultaneously we need to make the 5-cell cages match up with the 4-cell cages. Right. How are we going to do this? I don't know. I think what we're going to have to do is to try and spot places in the grid. Yeah, I mean, it's very tempting for me to believe that this is a 9-cell cage. It almost has to be. Hang on, let me just go back to the rules. Each cage has exactly one partner. So if I could prove that that made a 9-cell cage, no other cage. So there couldn't be another 3-cell cage that contained these 3 digits, because that would indicate that there were 2 possible cages that this could combine with. No, sorry, and I'm getting distracted from my own chain of thought here, but my thought was, very simply, by Sudoku, those 2 digits can't appear in that 6-cell cage. So if we were to highlight just these cells, you see these purple cells here, they definitely are 8 different digits. So all we have to conclude is that this cell is not in here. And it certainly can't be there, but I mean, if that cell, no, it's not actually, no, it doesn't quite work, does it? I can't immediately see why that would be. Wait a moment. Hang on. I'm actually going to look at this. I'm thinking that that causes... no. All right. Okay, I'm wrong. I'm wrong. I'm wrong in a good way. I'm wrong in a good way. This cage is not this one's partner, actually. And the reason that we can see this, it's not that easy to see it, but it's not too bad either. Imagine this was a 9-cell cage. What that causes in the grid is roping. Now, what do I mean by roping? Well, we could ask where these 3 digits go in this box. Now, on the presumption, on the hypothesis that these 3 digits join to this shape to make a 9-cell region, those 3 digits could not repeat in these 3 digits. So these 3 digits, let's do that, because otherwise we're going to get a bit too colourful. These red digits here, the only place they could go in box 2 would be in these 3 squares. But then by Sudoku, these red digits would go in these 3 squares. And that's not possible because of this little cell. If that little cell is transposed into one of these 3 cells, which it would be by Sudoku, then this cage, this blue cage, has the same digit in it. It has a repeated digit in it. So that's wrong, or roggen. That's another feature of yesterday's video. So what that's telling us is that these squares are not the counterpart of this. Actually, I might just leave these as purple, just to say this is the cage I'm focusing on for a moment. So those three squares, can we prove that they are or are not? Are they purple? No. Right, those are not purple, because these digits would have no possible fill, would they? How can I show you that so that that's clear? I mean, is that clear? I think it's clear to me. Maybe the way, look, the way to do it is to, let's just put some placeholder digits in here. So I'm just going to put in some digits. 1, 2, 2, 3, 4, 5, 6. I'm not saying these are the numbers 1, 2, 3, 4, 5, and 6. I'm just saying that they are. I mean, we could have done this with letters A, B, C, D, E, F, and nobody would have. I'm just trying to show you why this is a problem. What are these cells now? On the presumption that these two cages join together to form a 9-cell region, these are obviously in some order 7, 8, 9 over here. But these two squares now have no possible Sudoku option. They can't be 1, 2, 3, 4, 5, and 6. They see all of those digits, and they see the 7, 8, 9. So these would have no fill. And that tells us that these squares aren't, well, it tells us this cage is not the spare purple cage. So therefore is that one the spare? I think this is where it's going to get much more difficult, because no, it's the same point actually. It's not more difficult, it's the same point. So again, let's imagine that these are 1, 2, 3. It doesn't matter what these are. The point is that these are the others. So if these were 7, 8, 9 in some order, what's that square? It's got no fill again. It's the same point. It's just sort of in a different, in a different dimension. So actually, we've got a break in here. We now know that these squares. We know that this and this. Actually, we could do this, couldn't we? We could actually get rid of all colouring and make those. This is a cage. I'm sort of tempted. I am actually sort of tempted to leave this in. Now the reason for that is odd. It's actually even in this case, because these digits are 7, 8, and 9 in some order. So the point I want to make at this juncture is that I could have chosen I could have put apples into this square, oranges into this square, limes into this square. The point is that it's undoubtedly true that each of these cells in the purple region contains a different thing at the moment. And I'm just using numbers because I find it easier from a Sudoku perspective. And the reason it's easier is look at this square. It's very easy now to see that this square is a 4, actually, by Sudoku. So now that's not saying in the finished grid this is a 4, but it is saying in the finished grid whatever this digit is will be the same as this digit. So this might be a way of solving this puzzle. You basically do it, and then we're going to use the thermometers to disambiguate the correct order of the pattern that we're left with. Yeah, I mean, this is not a stupid idea. This is not a stupid idea because, again, I'm going to look at those two squares. And now, what are these two squares? They see 1, 2, 3, 4, 5, and 6. So they are from 7, 8, and 9. And I think that would have been hard. So in other words, 2 of these 3 digits go there. Now, I think that would have been hard to see if I hadn't done this hypothesis of just making these, or using placeholder digits. That square sees the 3 high numbers and 1, 2, 3 and 4, so that square is 5 or 6. Okay, this might be where it gets harder. Those 2 squares are 7, 8 and 9 on this hypothesis, aren't they? Because they clearly can't repeat anything that they've seen in the purple cage. But, oh yeah, now hang on. So this square is 1, 2 or 3. And we know that because we know that if this was 7... Well, there's two reasons we know that. If this was 7, 8 or 9... we proved there was roping, and that's going to break this cell. This cell is going to repeat in this cage. So we know that can't be true. The other reason we know that can't be true is there's only meant to be one partner of this cage. So if this was 7, 8, 9 and this was 7, 8, 9, we'd have 2 partners, and I think that that's against the rules. Each cage has exactly 1 partner. So that square is 1, 2 or 3. And therefore that digit goes in one of these 3 squares. Oh, 4. 4 is in one of those squares. That's very true. 5 and 6 are in these squares. That's obviously because 5 and 6 in box 1 have to be in those squares. And when we're doing this, so what I'm not allowed to do is to use the thermos. So I can't say there's a 6 here, so this has to be 7, 8 and 9. That is completely bogus, because I have no clue what in the final solution this digit is going to be. Right. I'm not quite sure now where I'm meant to look next. Sorry if you're seeing all sorts of things. I'm just... Am I meant to now try and link another of these 3 cell cages together with something else? Or am I meant to try and do... That looks a bit tempting, actually, but the thing is, I don't know. I could start filling this in with 1s, 2s, 3s, 4s and 5s, but they would have no relationship to these 1, 2, 3s, 4s and 5s. No, that feels wrong. That doesn't feel like the way to do this. The way to do this, I think, is going to be to somehow extrapolate from what we've actually already learned. So... maybe this cage. That has got no... Well, it could have 1... Well, hang on. Hang on. This cage... I mean, by Sudoku, for what it's worth, these 2 digits are clearly 2s, 3s, 5s and 6s, aren't they? These 3 squares can't be 7, 8, 9, so, I mean, in an extreme good-living world, these are 1, 2, 3, 4, 5 and 6. Those aren't 2, I suppose. That's just pure Sudoku. That's saying nothing else about these digits. What I'm trying to get clear in my head is whether it's legitimate for me to say that this can't be a 1, 2, 3, 4, 5 or 6. And the reason for that is that if that is not 1, 2, 3, 4, 5 or 6, then clearly it's 7, 8 or 9. And it has a mirror down here. But more importantly, well, not more importantly, well, although, actually, hang on. Actually, maybe there's a different way of thinking about this. Maybe there's a different way of thinking about this. Okay, so this 6-cell cage has got 5 digits in it, at least, from the panoply of digits that are low digits. So 5 of the 6 digits, and possibly 6 of the 6 digits, but definitely 5 of them are 6 or lower. And that means we have to pair this up with a green cage that contains at least 2 of 7, 8 and 9. At least 2. Now that cage can't have 2 of 7, 8 or 9 in it, because 7, 8 and 9, well, 2 of them are there. So this cage, it's going to join to this one, is it? That feels like what's got to happen. I just can't quite prove it in my brain. So the other option, either this joins this cage, which looks so natural, doesn't it? It's got 2 high digits, and then it's got that digit. So that would have to be a high digit to make the 3 high digits for the overall 9-cell cage. The only way that that is not a 9-cell cage is if this cage contains 2 high digits and 1 low digit. It can't contain 3 high digits because that digit can't appear in this cage. And then if that was true, that digit would be the same as that digit in this column. Whoa, this is really confusing actually. This is hard. This is definitely, well, I shouldn't have expected anything else. Bother. How can we disprove that that's got 2 high digits in it? Do I know something about that digit? That digit goes in that cage. Ah, that's lovely. That is absolutely lovely. Yes, I don't know what this digit is, but I know its properties. I know its highness. Right. Let's think about this digit. Where does this digit go in this box? And the answer is we don't know exactly, but it doesn't go in those 3 squares and it can't repeat in its own cage. So this digit is in one of these squares, yet it's not 5 or 6 because 5 or 6 are in these squares, so this can't be 5 or 6. So this is the other digit left to complete this row. And you can see that that's whatever of 7, 8, 9 is not used in this row, because these squares obviously plus the 5 or the 6 are all 8 digits except for whichever one of 7, 8, 9 has not been used in the row yet. So that's in that 7, 8, 9 digit is over there somewhere and must be the same as this digit. So that digit's a 7, 8 or a 9. And why do I love that so much? Well, the main reason is that that stops this green cage now containing 2 of the digits 7, 8, 9. Because if it had 2 of the digits, which it would need to have to marry up with this cage, there would be 4 digits in this column selected from 7, 8s and 9s, and that cannot be true. So now what we've learned is that this cage is the same as this cage. So we can colour those. We'll do that, yellow. Now we know this is a 7, 8 or a 9, which is what we suspected before, but is now proved because we need 3 7, 8s and 9s, obviously, in any combined cage. Now what do we know? What's the relationship? Is that digit's the same as that digit, isn't it? Whoa, this is going to get very complicated now. Well, it is, but it's important, I can see. Yeah, because yellow, if we go I mean, this digit can't reappear in yellow, otherwise yellow has 2 of this digit in it. So in this box, that digit must be the same as that digit. So let's label those with A. These are both the same digit, and now we can ask where that digit goes in this box, and the answer is exactly there. So these digits are the same, and they end up, okay, and they end up in there, which makes sense. So this actually is, I'm going to replace this pencil mark. This is a 5-6A triple. So these digits, I wonder if I call those B and C. I feel like that makes sense, actually. I don't know if we need to do this, but I'm going to do it. So this we'll call B and C. So now we've sort of labelled individually all of the 7, 8, 9 digits, but we don't know how they relate to this down here. I'm not sure if this is the right way to do it, but I'm going to try this pro tem and we'll see how we go. Can't use the thermometer. Don't even think about you using the thermometer, Simon. Right, so what do we know now? We know that, well, it's a very small point, but we know that 4 in yellow is in one of those 3 squares for sure. And that means 4 is in one of these 3 squares for sure, by Sudoku. Yeah, that's not the most brilliant deduction in the world, is it? 5, 6 and A. This still has to find a friend, doesn't it? Oh, it's totally straightforward. This is brilliant. This is brilliant. So far, it's not absolutely monstrous. Okay, what is the counterpart to the 5, 6A cage? Well, it can't be a cage that's got A in it, and that one's got A in it. So that's got to join up with that. Oh, that's absolutely fabulous. In fact, what I'm going to do, therefore, is we might as well make all of that green. And then we can make this one a different colour, can't we? So that one is therefore all grey. So let's make that one all grey. And 5, 6 and A go in this one. So this cage, I don't know whether to label it up. It is actually 1, 2, 3, 4, B and C in some order. And you can see that can't have B in it because of this. 4 comes out of those ones by Sudoku. 3 comes out of these ones. This is going to get complicated. If this gets much more, you know, if there's much more stuff going on than this is going to get very, very complicated. Yeah, sorry, I'm not seeing anything now. I'm not surprised. I'm actually quite surprised we've got this far this quickly. So I've got these A's dotted around the piece, haven't I? A can't go in there. Nearly. So A actually is quite restricted in this box, because that is A. So A goes down there. So A is in one of those 3 positions. So A is in this little cage. And that has to join with a blue cage. And that blue cage can't contain A. Does that one have... That one's got A in it, because that's A. So this one doesn't join to that one, for what that's worth. That one... This one doesn't have A in it, so it could join to that one. Because that's A, isn't it? Those 3 are all the same digit. Right. Oh, here's a tiny point which I will make. These squares are from 1, 2 and 3, just by Sudoku in this box. Right, yeah, okay, well that is something. Because where do these two digits go in this column? They can't repeat in the grey cage. So they've got to go down at the bottom here. So there's a 1, 2, 3 triple in this column. Which is of potential interest. Maybe. So those two digits, whatever they are, they go in 2 of these 3 squares. So one of these digits is high. Golly, this is very complicated actually. Very much is complicated. Okay, let's try that digit then in this box. So that digit is a 3, and I think it seems to have to be in those 3 squares, doesn't it? I don't know which one, but it's in one of them by Sudoku, and then it can't repeat again in yellow, so we could take 3 out of these squares and place 3 in column 1. That feels like a win. Now what does that do? I don't know. There's now, okay, in this column now, there's definitely a 2 in this domino, but we seem to have already removed 2 as an option from the rest of the yellow cage, so that might not do anything. I've got to put... Oh, it's nearly interesting. I just can't quite see how to do it. There's also sort of almost the weirdest, like, quintuple in box 8, made up of the digits 1, 2 and 3. And these digits, which can only be from 1, 2, 3, 4, B and C. So I know this has got B and C in it. Oh! Of course, yes. All right. Well, here's something. These digits are effectively an ABC triple, aren't they? So those digits can't be B or C. Sorry, that's totally obvious. I'm not actually sure that's going to do very much. Well, okay. So B in the green cage now is in this domino. So let's label that. And that means B is in one of those 3 squares. Bobbins. I don't think that's done it, has it? I've got 4 labelled in yellow here. Why is that? No, that's fair enough. So that digit, yeah, 4 has to appear in the yellow cage somewhere. It's not in this top bit, so it must be in the bottom bit, and it can't be in those squares, and it's not that one. So 4 is in there. So this has got 4. Well, 4 is in there, so it's not in here. So this is a 1, 2 pair, and that might do something. So I can take 1 and 2 out of all the rest of the green squares. Oh, come on. Well, now 1 has come out of these squares. So what does that mean? So, oh, this is useful. So now yellow on the bottom side hasn't got 1 in it at all. So yellow on the top side does have 1 in it, and that's a 1. And now 1 goes over here and joins its friend the 4. So these 2 squares are a 2, 3 pair, which were the same as those 2 squares, which were a 2, 3 pair. Now 3 comes out of all of these squares, and this is a BC pair, so that is a 4. This is absolutely mad. Oh, goodness me. This is just beautiful. Now that is a 3. It's just forced to be. It can't be 4 and it can't be C. C's already appeared. So that's a 3. Look at the way you can disambiguate all of this. It's absolute nonsense, and yet you can actually find a way through this. So, look at this green cage. We've literally placed almost every digit in it. Yeah, see, it's interesting. I wonder whether having these as 7, 8, 9 is sensible, or whether it would be better to make that an ABC triple. I don't know. I'm just looking at it, thinking, how am I going to really resolve these things? Right. Okay. What's that digit then? So there is definitely a 3 and a 4 in here. So 5 or 6 is in this triple, which means that's the other of 5 and 6. And that's in a blue cage. Well, oh, I see. Oh, no, that is interesting. That is interesting. Okay, so this digit, I'm running out of letters, aren't I? Let's go to D. That digit, where does that go in this cage? Now, you might say it could be that one. I don't think it can be that one, because that digit can't repeat in its own cage. So it's not in those squares, so it's in one of these squares. So this is a 2D. 2 and D, and therefore D is there because it's 5 or 6, which means this is 7, 8 or 9, and these are a BC pair. I'm going to put that in. I'm not sure if I can disambiguate it. So these 2 digits are the same as those 2 digits, which I think we already knew. Okay, what does this mean? Where is 1 in this bottom box? And the answer is I don't know, but it's in one of those squares, I think. A. Okay, so this is 1A. That's not 4. I think literally I've got to be very diligent, if I can be, about every single digit here. 2 is a sort of X-wing, isn't it, in those 4 cells? In other words, we can ask where 2 goes in row 7 and see it's not in any of these 6. So 2 is over on the right-hand side of the grid. Okay. Oh, wow. Yeah. Look at the grey cage now. Now the grey cage apparently already contains a B over here somewhere, which must be because, yeah, it's because of this, and therefore that filters through, doesn't it, to this square, and that square cannot be B because B would appear twice in the grey cage. So that one is C. Which means that one is B, which means B, so this now is known. These 3 digits are a B and a 1-4 pair. Yeah, but we can sort of almost, that was almost obvious, I think. And these squares are C and a 2-3 pair. Yeah, but this should all help, shouldn't it, when we're trying to work out which cages these all go with. The more context we can get into all of these 5-cell cages and 4-cell cages, the more we can rule out possible partners. Okay. So we've now, I wonder whether the idea now that we should pursue is to pencil mark these 2 digits. Because we can because these two digits here, which are in the grey cage, can't be a high digit. All of those have gone. They can't be 2, 3, so they must be 1, 4, 5, or 6. I don't know if that's helpful or not, but I'm going to quickly pencil mark it. I mean, obviously this one can't be 4 or 6 now because of this. So that's 1 or 5. This one can't be 4, actually, or 1. Why can't it be 1? Oh, because it's got a 1 looking at it. So this is 5. Oh, that's 5 or 6. That's 5 or 6. That's 3 by a process of sudoku. So that digit is the same as that digit. Because we know that D is in one of those, so what's not D is there, and that's also not D, so we're going to make that E. Oh no, I don't want to do it like that, I want to do it corner pencil mark. Those two are E. Okay, alright, so where I see, so where now is 1 at all in this grey cage? It's only got one possible cell it can be in, so that's a 1. Where is 1 in box 4? And the answer is 1 exact cell right on the thingy thing of a thermo in the bulb. It looks like it's in its right place. So 1 is in one of those squares. Where is 1 in this bottom box? It's got to be in the corner. So these are not 1. Right, so this is 1, this is 2, that's 3. So 3 now is in one of these 3 squares, not in the corner. No 3's in the corner today. Although there is still a chance we get a 3 in the corner, because it might be that 1, say, in the correct, once we've permed all the digits, is actually a 3. So we could get a 3 in the corner. So it's maybe not a bad thing we haven't got a 3 in the corner. 2, 1, oh, 1 is up here as well. So, oh, see, this is like an AD pair, isn't it? So this is D, so E is down here. This is 4 and E. And this is A and D. But surely I must now know what this column is. What's that digit? I must know that. What's D? D is... Oh, no, hang on. Hang on, don't I know now what D is? Because DC is a 6. Yeah, I think that's right. D is C. I know D is down here, and it's C6. So D, which is that one, must be 5. So that's going to allow us to do some thingies. Let me just unwind that again. So that E is 6. So E is that one. Right. So we take 5 out of these. We put 5 in here. This is 5. This is 6. This is now A and 5. So let's switch to central notation. That's A5. I think there's going to be a lot we can get from this. 6 is now moved over here. Let's get rid of the 4 in the corner there. Do we now need the E? I think... No, we don't, do we? Because once we get rid of the pencil mark there, we've effectively rendered D and E otiose, I think. I might be wrong, but I don't see a need for them anymore. Wow. Okay, and we still have this question. What's that digit? That digit is not A and it's not B, so that digit is C. So this is a 789 digit, and it is C, but I don't know what C is yet. Now, what next? I hear you chorus. And the answer to that is I don't know. But I do know the composition of these, don't I? I've not put in 4 and 5. So this is 4 and 5 and B. That is actually what it is. It's 4, 5 and B. Let's put B in the middle, and then we can get rid of the B corner mark. That's 4, 5B. That's C. So I must know what these are. These have got to be 2, 6 and A. Okay, well, let's put that in. 2, 6. Sorry, I need to go to the right things. I'm mixing between numbers and letters. 2, 6 and A. And that's all in a cage, look, with a C. Now, if I could get that digit, then I would know exactly what was in that cage. But, well, do I know that digit by Sudoku? Must do. I've not put C into this column, have I? I don't think I have. So that's a C, which is, I want to put that in the corner and label that with 7, 8, 9. And these digits, let's get rid of the 4, because we now are very sure there's a 4 in here, are 4, 6, and a B. So this is a 4, 6B congregation. Now, what can we do from a Sudoku perspective with that? We can get rid of 6 from this square, because 6 is already definitely in one of those squares. So that's not 6. That's nearly good, isn't it? But it's not quite good enough. We can get rid of A from this digit. That can't be A because it C's A. So this is 2 or 6. Can we get that? Is that seeing somehow a 4? No, I don't think it is. I'm not sure. Oh, I realise I've just stopped talking. I'm not meaning to stop talking. I'm just trying to spot. Maybe now I've got to think about, what about that one? I actually do know what that is. That is 3, 4, 5, 6 and B. So I need to find a 4-cell cage that can be, let's get this right, 1, 2, A and C, I think. So which 4-cell cage? So we need an orange cage that could be 1, 2, 4 and C. Oh, this is going to be very difficult, isn't it? Well, okay, one thing it's not is that one. Because that can't have a 1 in it, so it's not this one. 1, 2, 4 and C. Did I say 1, 2? What did I say? 1, 2, A and C. Ah, so it's not that one. That was nearly it. 1, 2, A, but 5 is the other digit, so there'll be 2 5s if we join. So it's not that one, and it's not that one. I want that one. Which one is it? 1. Oh, it can't be something with another 3 in it. So it's not that one. Right, so we're down to 2. This is quite exciting. I don't know what. Well, if it was, no, it can't be. It can't be this one. I don't think, because 2 of the digits here are from 4. Well, one of them can be the correct digit. We need a 1. So let's imagine one of these was a 1. The other is a 4 or a B, and both of those appear in that one. B there, 4 there. So it's not this one. It wasn't this one, so it must be that one. These two are a pair, I think. That felt logical. Now, we've got to choose a colour, which is going to get more and more difficult now. I haven't used red, actually. Or maybe light green. Light green is a bit less offensive, isn't it? Let's use light green. So, we now know that these squares are 1, 2... Let's actually just put it in. 1, 2... A and C. Now, what on earth? That's not 1 or 2 by Sudoku. That can actually be all of those things, I think. This one. C's A. Oh, if that was a 2, we'd have a 1C pair. That would make that A. It's getting quite hard to scan this actually. 1, 2, C. 1 A or C here. Oh, I see. No, all right. Okay, so here is an interesting thought. I think this is important actually. At the start, we put 7, 8, 9 in here, knowing that they were an ABC triple, but not knowing the order of them. So what I can do here is I can delete these and write ABC. And now look at this row carefully. There's an ABC there, a BC there, and an AC there. They are the 3 high digits in the row. So that square can't be an A and must be a 5. And that is an A. Now, do I make that big A, or I don't know what to do. I'm going to make it, what am I going to do? I'm going to make it A in the corner and 7, 8, 9 in the cell. So this square is not now able to be A. And if this is 5, do I literally get nothing from that? I get there's a 5 down here. That's rotten. I thought that was going to be great. Oh, sorry. Okay. Well, that has not proved to be the most brilliant deduction in Christendom, has it? Maybe that was not the way to do that. Right. So we've got a green cage, approximate, well, actually placed, but it doesn't seem to have done very much. Do we actually know exactly? We do know exactly what's in that one. Now it's 4 cells rather than 5 cells. But it is 1, 2, 5 and A. So there must be a 5-cell cage in the puzzle that can be 3, 4, 6 BC. 3, 4, 6 BC. Which one is that? 3, 4. Oh, well, it's not actually. It's not this one. That's got 2. That would have 2 5s in it. 3. Oh. Well, hang on. No, that's got a 2 in it. Definitely. So it's not that one. So it's not these two. This has got a 2 in it. So it's not. This is actually not as bad as I thought. I think it's got to be that one. I'm just going to double check that because that felt remarkably smooth all of a sudden. 5 would repeat. 2 would repeat. 2 would repeat. So it's this one. Good grief. So this is. We can get rid of this and colour it its own special colour, which we'll have to make red now because I'm running out of colours. So, okay, so when we disambiguate the last 2, or is it 3? Have I got 3 left now? Bobbins, I think I've got 3 left. I have got 3 left, haven't I? So I'm going to run out of colours. Is there a way I can get round this? I'm going to have to use... No, the other thought is I'm going to have to use the whole palette, which is going to include my black colour, which I never like using, so I might switch the black colour out. But anyway, what do we now know? We know this cage, we know its exact composition. It is 3, 4, 6 BC. So let's just fill that in. 3, 4, 6 BC, and see if we can get rid of anything. Get rid of 3 from that one. Is that all? 3, 4, 6. Oh, that's quite interesting. Right, that's big. So this is not 1 or 2, is it? It's B or C. And then I've got a BC pair, which gets me A there. That's a win. Right, how do we do this? I'm going to keep having to switch between letters and numbers, which is not proving very successful. So this is definitely 7, 8, 9. It's definitely A. That square now can't be A or C, can it? Because we've got this ABC triple. So this is 1 or 2 only. What's that? Is that 1 or 2 now as well? Yeah, I think that must be true. And this is B or C. So it's the same as this, which is the same as this. Now, can we do any better? 3 comes out of both of these squares because of this 3. 4, 6, B, C. So whatever that is has to go in one of these two squares. Wow. Oh, is that right? Okay, this might be right. I seem to have a 1, 2, C triple in this cage, which means that square is the only square that can be A. Yeah, that feels right, actually. So that's A, not 3. So we need to correct all pencil markage in this. So this is A, which means... Oh, well, we already knew that wasn't A. Sorry, that was totally obvious. Okay, but B and C are now looking at that square. So this has come right down. This is 3, 4, or 6. Which must mean this square... yeah, I see. Where is 3 in this row? And that 3 knocks a 3 out of this square, which I should have seen before but didn't. And I think 3 has to be there. So this... no, that's not done it, has it? Well, alright, that takes 3 out of that square. Wow. Wow, okay. 4... Oh, right, so now in this row, those squares... Where's 5? 5 can't go in red, can it? Or is that wrong? No, 5 can't repeat in red. Right, there's an easy win for us that I didn't see. That's a 5. So this is not a 5, it's a 6 or an A. That's not a 1. Oh, no, that's great. Is that true? I can't... That is true. So 1 in green is in the top here. So that it's not there. That's got to be a 2. That's a 1. So, oh, this is going to do all sorts of things. Right, so 2 comes out of these. These are a 1C pair. I don't believe it. Well, it means that's not C, I suppose. We'd take that small win. So this is really confusing. I mean, there's like 4, 6B. Where's... No, I was about to say where's 5 in this row. That's not a good question. I think there's something going on in this row. I just can't get my head around it. Alright, but if this is a 1C pair, do we get anything better? Oh, yeah, we get a 1 here. So this is 1. This is now C. So how we're doing that with a 7, 8, 9. No, a 7, 8, 9 in the cell and a C in the corner. And 1 is now exactly there in this top thingy. So these are now 4B pair. We've placed all of the 1s in the grid, although obviously these are not going to be 1s when we have to do the permutations. Now... What's this? That is a 4 or a 6, I think. Because it can't be a B or a C. And everything else is placed. So that's a 4 or a 6. But we haven't found a friend for this one yet, have we? So that digit is the same as that digit. Oh, well, hang on. That sort of feels like it's important, because that would tell me this wasn't a B. For what that's worth. Is that right? So what I'm saying is that digit, we know that this is a 4, 6, BC quadruple. But that 4 or 6 needs to be in one of those two cells, therefore it can't be that one, which apparently is B or C. So it must be that one. So this one is not B. and these two are the same. So maybe I've got to give those a letter again. Now, did we use up D? I think we used up D, so let's reinstate D. So D, oh no, we don't quite know, because D could be 4 and could be there. So, oh, hang on. So where is D in this box then? Maybe that's a better question. It's got to be here. So that's D. Ah, that doesn't matter though. D is 4 or 6, so it's in either of these squares. Bother. So D and D are there. So D is in one of these two squares. Ah, I can't quite see how to do it. Botheration. Okay, sorry. Right, where were we? We're floundering around trying to figure this out. How long have I've only had an hour. That's not too bad. That's not too bad. Come on, Simon, you can do this. Just have some inspiration. 2 comes out of here by Sudoku. Can we do any more Sudoku? It's sort of unlikely, although it's exactly the sort of thing I might miss. And the other thing I mustn't neglect, of course, is that there's no harm. I mean, I haven't managed to find a home for... no, that's D. We don't know exactly what D is, do we? Yeah, I don't know what these are, but maybe... I've not found a home for that one. That seems quite... Oh, yeah, well, actually, this is easy. This one... Have I really not found a pair for that one? I don't think I have, but it's got a 1 in it. So that one's got a 1 in it, and that one's got a 1 in it. So I think this one has to join with that one. That feels right. Now, which colour? Okay, we're going to go off palette here. We'll go to brown for that one. And then when we disambiguate the last 2, we'll make one of them orange and one of them blue. And now let's actually just try and do that straight away then. Yeah, there's some interesting thoughts here actually. Sorry, I'm sort of jumping around in my brain. But one thing is that 5 appears in brown on the left, so 5 can't appear in brown on the right. And therefore 5, I think, has to be in one of those 2 squares, and therefore 5 is actually placed exactly there. And that is not a 5. And that is a 4B pair. Oh, come on. Well, 5 goes in the corner of the grid by Sudoku. So this is a 6A pair. Now, we know that's A, do we? I think we do. So this is A, and that is 6. So that's a 6. That is an A, which we're doing like this. So A, which one is A? Oh no, A we don't know. Oh no. So A is in one of these squares, but we don't know which one. The 6 comes out of that square at the bottom. 3 maybe, yeah. Where's 3 in the world? 3 is in one of those 2 squares in box 6. But we already knew it wasn't in brown. C is there, C is here. We don't know. We can't put D. We can't put D in brown. In this box. So D must be in brown in this box, and D is there. So one of these is D. And that's D. So that's D. Okay, that might be good. D is a 4 or a 6, so this is not B. And it still doesn't disambiguate, I don't think, but it's mild progress. Okay. Oh, Simon. Come on, concentrate. Maybe I do have to keep trying to disambiguate all these other cages. It's just I'm not convinced I'll be able to do it. Hang on, I've lost track of what's going on here. Oh, see, I've got 2 blue cages left and 2 orange cages left, but they have very common digits. Oh, that's rotten. So, oh, hang on, that one's got 3 in it. Is that right? That one has got 3 in it, so it can't join to that one. So this one joins to that one. Right, okay, so that means, let's go back to my original palette. I can make these blue, and I can make this orange. And there we have unbroken the secrets. And that means that we have a... what does it mean? I don't know. D is here. Is there definitely a 6 in there? There is. Yes, orange has already got a 6 in it. So that must be... So D is 4. So D, wherever it occurs, is a 4. So that is a B now. This is not 4. This is not 4. That becomes a B, which is a 7, 8, 9. This becomes a 4 by sudoku. 4. That becomes a 4 by sudoku. I mean, if this works, it will feel completely and utterly magical if this works out. All of this nonsense we've been doing with these letters and things, it's really... I've been very surprised at how well it seems to be working. Oh, come on. So 4s. Have we got all the 4s in the grid? No. No, that's a 4 because it's B. D, sorry. So now we get all the 4s. Now, could we do... We can get the 6 here. Now, so that's a 6. Because that has to be a B, apparently. Yeah, because there was 6 in there. That makes sense. So that's a 6. So that's a 2. And if that's a 2, that's a 2. And that's a 5. And therefore that's a 5. And that is a B. And again, it looks really good, doesn't it? Oh, my phone's buzzing. That is okay. Okay. Now, what about that? That's a 7, 8, 9 triple. So that's not able to also be C. And we haven't put into this column 2s, 3s, and 6s. No, come on. Where? Oh. Yeah, this brown cell. So in this column, we've got 2, 3, and 6 to place, but that square is not allowed to be 2 by sudoku, and it's not allowed to be 6 because there'll be 2 6s in brown. So I think that's got to be a 3, which means this is a 2. This is now actually a C, which means this is a 3. And if C, we know we've got to go back to this business of doing this. And if that's C, that has become B now. So that's something. We get a B, and we get a 7, 8, 9 here. And if that's B and C, that is a 6 in the corner. And, oh, okay, so what's this? Oh, is that just B or C? Oh, it's not B, so is that C? Yeah, that looks like it has to be C by a process of elimination. So that's C, and it's 7, 8, or 9. And in this column, we have never put a B, so that must be B. 7, 8, 9, B, let's label it up. In this column, we've never put 6 in, which apparently has to go there. which means that's a 6, and this is, you've guessed it, an A. So those are a triple. We've not put in 2 in this row, so 2 goes here. And now in this column we've not put A in, so A goes there. So actually, have we done it in a sort of weird way? No. Oh yes, no, we have, because I know the order of this. That's got to be the B digit. So, what do I mean when I say have we done it? Well, I think we have done it in the sense that, let's make that C. Let me show you why I think we've done it. Because now that being B puts B in, that's B in the corner, that's B in the spotlight, losing its religion. Right, come on, that is a B in the corner by Sudoku. So we put B, we put 7, 8, 9, that's therefore C. How many clicks am I having to do this? It's a lot, it feels like a lot. C, where's my C? I need to put C in the corner. Okay, now, I think, and I might be wrong, I think I've got 1, 2, 3, 4, 5 and 6 positioned in every box. And what's more important, I've got the A's, B's and C's disposed in every box. Now, in other words, what I can do at this point is these are arbitrary. Everything, this is the important point to realise. Everything in this puzzle is arbitrary. All these placeholders are doing is saying that this digit is different from these and different from these. So whichever one of these I make 7 now, you can see if I make that one 7, then I make all the C's 7, because I know where all of that digit goes around the puzzle. So we might as well make this, let's make that 7, 8, 9. So if that's 7, then all of the A's, let's not get this wrong, that would be a disaster. All of the A's, all of those digits, have we highlighted 9? Yes. All of those I'm going to say arbitrarily are 7. I could have made them oranges. Yeah, wouldn't change the point. The point is that that cell is propagated around the grid into those positions. Now C is the next one. So C, 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 Nori, C, C. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's make those 8. That would be sensible. And then the only remaining thing is to allocate 9 to the B's. 9. And now what we need to do, now we can see that we didn't luck in on the right answer, in the sense that I'm looking at this thermometer and it is telling me that the 9, the thing that we're calling 9, so imagine it was the letter I, is a lower digit than the thing that we're calling 8. So what we now need to do is to somehow use the thermometers in the grid. So perhaps I can't really see the thermometers very well. So what I'm going to do, I think, there is no value for me keeping these cages the same, is there? I don't think so. So what I'm going to do, Control A, I'm going to undo all of the colours. Right, that is better actually. I can see that fairly clearly. So what we're looking to do now is to use the thermometers. Now I wonder, no, I thought maybe, knowing Sved, if I clicked all the bulbs or something, maybe it would just highlight them all for me. Maybe if no, I'm sure it doesn't work. No, it just highlights the digits. So how are we going to do this? What we're going to do is we've got to somehow trace through these thermometers. Maybe if I highlight all the bulbs in one colour, that will at least give us a clue. And we'll highlight all of the tips in an, oh, that's not, no, that's an that's an even digit. It's clearly wrong. That's a 7. All of the tips in a different colour, like that. Yeah, okay. And we've got 2 even digits as well that I haven't really thought about at all. But the what are we now being told about the remaining digits? Wow. Okay, there's one thing I can see here, which is odd. Okay. I can't use this fact, annoyingly, but I can now tell you I believe that 1 is correct and 4 is wrong. I think 4 is 9. I might be wrong about that, but the reason I think that must be true is I can't see the digits 1 and 4 anywhere else in the puzzle. So how could you ever distinguish? So how could 4 not be the top digit is what I'm thinking about. If 4 isn't the top digit, it would need to be involved in this sequence of thermometers somehow to disambiguate it. That's what I think anyway. I think that what we're going to find that 1 is low and 4 is high. And we've got 2 digits that are definitely even. So these 2 digits are definitely from 2, 4, 6 and 8. Now, okay, so 7, no, 7 appears once, I think. Does 7 appear once? 7 never appears in the tip of a thermometer. It's never purple. 7, okay, so 7 is less than 9. Oh, you know, I might need a pen and paper to do this. This is confusing. 7 is less than 9. 9 is less than 6. 6 is less than 2. Okay, so 7 is definitely less than 2. So this is not 2. And 7, which is even, once we've done the transformation, is not 8. Hang on, so 7 is less than 9, is less than 6. So 7 is less than 9, it's less than 6, it's less than 2. 2 is greater than 8. That's, I don't want to think. Oh no, but 6 is less than 5 as well. 5 is less than 3. And 3 is less than 8. That is interesting. Okay, let me try and think about that again then. I don't know how to do this in terms of tracing this through, but I think then I got onto a very long sequence. I'm going to try and disprove that 7 can be as high as 4, because I know that 7 is even. And I also know, or I think I know, that 7 is quite a small even number, because I've found so many digits that I think have to be higher than it. So let's work with the hypothesis that 7 is 4, and if we can disprove that, we know 7 is 2. So if 7 is 4, we know it's less than 9, so 9 would therefore be 5. We know 9 is less than 6. Oh god, this is confusing, isn't it? So 7 we said it was 4, so 9 is 5. So 6 is 6 now, so 6 is 6. But 6 is also less than 5, so 5 is now 7. So 3 is now 8. And 8 is now 9. And 2 is 10. So there's too many digits. There's too many digits. So 7 is the digit 2. Oh, I've got it. Okay, and that sequence that took me all the way through to 2 being at least 10, well, if we take that down by 2, so we start with 7 being 2, we could have run that sequence again, and that would have told us that 2 is at least 8. Well, 2 cannot be more than 8 because 2 is even on the other side. So 7 is 2 and 2 is 8. and we actually know exactly what the digits, how the digits move in between, because there is a continuous sequence of thermometers. Okay, and this is what's proving that 1 and 4 are actually the digits 1 and 9. Because, right, I'm going to try and articulate this clearly, but it is now clear in my brain. So we have proved that 7 is 2 in the finished grid. We've proved that 2 is 8. And we have a sequence of thermometers that link every digit between 2 and 8 to a number in this grid. And therefore, the only options for the digits 1 and 4, for this 1 and 4, are the digits 1 and 9, which have not been mapped to anything yet. And this thermometer tells us the order of those. So we can only map the digits 1 and 9, but we're told that 4 is higher. So 4 is mapping to 9. Right, this is going to be really difficult to do. It's going to be really, really awkward, isn't it? Because what I now need to do is to double-click all the 4s and turn them into 9s. But at the same time, I need to remember that the 9s... how do I do this? I need to... The 1s are okay. So probably what I have to do is double click the 9s first. Oh no, that didn't work. Double click the 9s first. So if we make the 9s into A's, for example, and now I can double click the 4s and make those 9s. Okay, so this is now sort of correct, although I'm now thinking this was a bad way to... No, this is the wrong way to start this. I'm going to go back. I think a much better option is going to be to work my way up from along these thermometers, actually. So I should start from 7, which I know 7 I know is the equivalent of 2, and 2 is the equivalent of 8. So maybe we start there. I'm not sure. 7 is 2, so I need to double click the 2s, turn those into A's. Now double click the 7s and turn those into 2s. So this is the start of a correct sequence. And now the A's, which are actually 2s now, although they used to be 2s. These are actually the 8s in the finished grid. So I need to double click the 8s and turn those into something else. Yeah, but then I've got to work out where 8 was on that sequence, haven't I? I think 8 was 7 because of that thermometer. Yeah, that's what I'm going to have to do. So 8, I'm going to make B now. Or is it B? Yeah, presumably it is B. And that allows me to make A's into the digit 8. And now my B's, which were the digit 8 in the grid we solved, I think from this thermometer, 7, and then 3 would be 6. 3 is bigger than 5, which would be 5. 5 was bigger than 6, which would be 4. 6, I'm sure there was one. 6, yeah, 6 is bigger than 9, which would be 3. And 9 is bigger than 2, because 9 is bigger than 2. So that is the order. Right, so B is now, we need to change this to be 7. Okay, well that's just going to work, isn't it? Because I haven't got any 7s in the grid. Okay. But then what's going to be 6? That's what we have to think about next. That's going to be 3. Okay, so we need to change these into 7s. And now we need to go to 3s and make those into A's, because they are going to become 6's, which means I have to go to 6's and make those into B's, and now I make the 3's into 6's, and now I needed to find where is 6. So 6 is on this thermometer. 6 is at the tip of this thermometer going down into 5's, which I don't think change in this grid. I'm losing track of everything I'm doing here. So the B's used to be 3's, didn't they? So when I put the 3's in, where were the 3's in the sequence? Oh, I almost do need to write this down. I'm sure that what the logic we found was correct. I'm now not sure I'm doing the transformation correctly. Yeah, 3 was bigger. We found the 6's, did we? I can't remember. Let me go back. Yeah, we thought 3. Oh, we thought 3 had to be 6. Okay, so we were transforming 6's. And when we're transforming 6's, we need to transform 6's, do we, into 5's then? So if 6's become 5's, 5's become 4's. Oh, I had this all sorted out in my brain, and it's just it's hard to do this without an aide-memoire. It's really hard to do it without an aide-memoire. I've totally lost track of what I was doing. I'm so sorry. I'm making a right mess of this now. Let's unwind and go back through what we did. So we highlighted those. We concluded that 2's had to be 8's, didn't we? So we did that transformation, and then we worked out 8's had to be 7's. I remember that. But to do that, we had to get rid of 7, and I can't remember. A 7 had to become a 2. Where have we done that transformation? Or maybe we did. Maybe we elided it over that, did we? Oh no, am I going to have to get out a notepad or something to do this? I don't normally have to do this, but I think in this instance, to avoid making an absolute ricket of this, it might be sensible to try and do it this way. Just so that I don't get this transformation wrong. I really don't want to. And I think we've understood the puzzle. We've just got to make sure we do the transformation in the right order. And as I'm changing the digits, I'm losing track of which ones I've changed and which ones I haven't changed. So hang on, let me go to Notepad. How do I do that? Notepad. You can tell I hardly ever use this Notepad. Alright, so what are we saying? We're saying that in the digits 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry, that's what I'm doing there. We're saying that the digit 1 becomes the digit 1. We're saying the digit 4 becomes the digit 9. We're saying the digit 2 becomes the digit 8. We're saying the digit 7 becomes the digit 2. We're saying the digit 9 becomes the digit 3. We're saying the digit 3, so 9, yeah, so then we need a 9 on the tip of the thermo. Because we're saying that 9, yeah, we're saying 9 is a 3. And then we're saying, which way round did it go then? I can't remember now. Oh, bobbins, bobbins, bobbins. 2, where is 2 in terms of these thermometers? Because we had a complete path, I know we did. I think it went to 6. Yeah, it did. It went to 6. So 9 was lower than 6. So 6 must be the equivalent of 4. And then 6 is lower than 5. So 5 must be the equivalent of 5. And then 5 is lower than 3. Oh, hang on. Oh yeah, which I haven't put in yet. So 3 must become 6. And then 3 is lower than 8. So 8 must become 7. Right, so this is the total transformation. So 1 goes to 1, 2 goes to 8, 3 goes to 6, 4 goes to 9, 5 stays the same, 6's become 4s, 7's become 2s, 8's become 7s, and 9's become 3s. With the left-hand side figures being as they're stated in this grid now. So let's now we might be able to do this without thinking so. Oh, come back, all is forgiven. I want to be able to see that as I oh, but when I click on that, it's going, well, maybe if I put it over there, then when I click on this, I'll still be able to see it. You might not be able to, and I apologize for that. Okay, so what we're now learning in the grid is that the digit 9 has to become, these 9s all become 3s. So let's change 3s into A's and change 9s into 3s. There we go. Oh, is that right? That's a real 3 in the corner. That's 3 in the spotlight losing its religion. Now the A's, which are now the original 3s. The original 3s need to become 6s. So we can highlight the 6s, change those into B's, highlight the A's, and turn those into these into 6s. Okay, now these 6s need to become 4s. So we click the 4s and turn those into A's, and these 6s, which are the B's, aren't they? They become 4s. Now the A's are now 4s, and they need to become 9s. Now, we've already done the 9s, so that's sort of going to be the end of one sequence, isn't it? So they become 9s. And that's sort of an internal cycle of this nonsense that we've actually completed. Now the 8s become 7s. So if we double click the 8s and turn those into A's, double click the 7s and turn those into B's, and make the A's now into 7s. And the 7s need to become 2s. So we now need to click 2s and make those into A's, and click B's and make these into 2s. And then we need to click the A's, which were 2s, weren't they? They become 8s, which we haven't got any left of in the grid. So that suggests we've now filled in all of the puzzle, I think. And the way we can check whether this works is we can go along the thermos and see, well, there's two things, isn't there? Firstly, is it a real sudoku? I mean, I can click tick and that will probably tell us it's correct. But I don't want to click tick until I'm fairly sure it's right. I just want to check these thermos. So do they all work? We've got 2 and 8 into the even cells. That thermo works. That works. That works. That works. That works. It looks like it works. Wow, what a puzzle that is. That is just amazing. It's absolutely amazing. And I think that this idea of using a placeholder approach was really important because it allowed me to see certain cells as being restricted in a way I think I'd have found difficult otherwise. Anyway, let's click. Yeah, you can. Puzzle doesn't include solution. Solve counter 3 in 131 days. So that's probably since Sven started keeping statistics. Only 3 people have solved this, basically, in a third of a year. I'm not that surprised. I mean, it is a hard puzzle, but perhaps not as monstrous as some of the other behemoths we've done recently, but it was every bit as clever. I loved it. I'm just trying to... How can I tell whether or not this is the... I mean, it's obviously from a sudoku perspective, correct? Though it's weird, so that 7, 8, 9 triple eventually became 2, 7, 3 down there, and you can see that looks correct, doesn't it? Actually, it really does. In fact, we could go through, if I can remember, and so this cage, which one did that join to? Was it that one? It looks like it's that one. They've got different digits in them. And then that one joined to, I want to say this one actually, and that looks good. And then this one I remember joined to that one, so that looks good. And now I can't remember the 5-cell cages very well at all. This was a 5-cell cage, and that needs to, so there's some cage in here that's got a 1, 2 and 1, 2, 7 and 8 in it. That one. So that looks okay, doesn't it? Providing we don't then find that this joins to another cage as well. This one is 2, 3, 6, 8. I can't remember which one. That one looks like it's good, doesn't it? So that's good. That's got a friend. This one is 1, 5, 6, 9. Ooh, can't see that one at all. Where's that one? 1, 5, 6, 9. There is one. That's good. It's good when there is a match. That one, okay, that one was close together, wasn't it? So that looks like, I think this is right. I really do. I think it's right now. I'm fairly confident. Oh yes, and that one joins to this one. Yeah, so I think this is correct. Absolutely brilliant. Totally normal cat. Managed to do it. Thank you very much if you've managed to stick with me, especially through the last 20 minutes, which was me floundering around trying to do the ordering correctly without making a mess of things. It must have been very frustrating to watch. I hope you can forgive me. And those of you who've asked for the puzzle, I hope that was what you were after. Let me know in the comments if you had a go. Let me know how you get on. Let's give TotallyNormalCat all the credit in the world. See actually if we can get them constructing again, because I haven't seen a new TotallyNormalCat puzzle for a long time. And we'll be back later with another edition of Cracking the Cryptic.